All right, so today we're going to talk about sorting and searching algorithms. There's different ways. Basically, what we're talking about when we're talking about sorting, what are we talking about? We're talking about like maybe you've got a list or a one-dimensional array of things, and you need to put them in order, right? So usually we're talking about maybe putting them in ascending order. That's from lowest to greatest, right? But you can modify the algorithm a little bit so that it would sort in descending order. That's from greatest to lowest, right? So either way. And so there's different ways to do this, and there's different sorting algorithms that have been developed over the years, and they work in different ways. Some of them are more efficient than others, or run faster. Some of them are easier to understand than others, right? So we're going to take a look at a few here. So I have some. If you look in the videos folder, I have some links to some videos. There's a class at Harvard. It's kind of like their introduction to computer science type course. It's a big lecture course, and they've got some good videos that they publish all their videos and stuff on YouTube. And so I really like some of these videos. They're really good. But I've got some here, some links. We're going to take a look at selection sort, bubble sort, insertion sort, and merge sort. So your book in the erase chapter has information and the code for selection sort, right? So that's one of my favorite ones as far as like these three intro type sorting algorithms. And then later on in one of the later chapters, I think they show some of these others like bubble sort, insertion sort, and maybe a couple of others. I can't remember if they have merge sort or quick sort in there or something. Anyway, so I'm going to pause the video and we're going to take a look at these other videos. If you're watching this video, then you should watch these videos first before you go on. So make sure that you watch the explanation videos first. All right, so we looked at all these different algorithms, right? And there's this website that I came across a few years ago that shows these sorting algorithms visually, which is kind of cool. And I have a link to this down here as well, sorting algorithm visualization. Let's take a quick look at that. And so this is what it looks like. So we can take a look at each one of these individually, or you can run them all at the same time to kind of see visually how fast they are compared to each other. So it's kind of cool. So if you just take something like a selection sort real quick, and you can change the size, like the length of the list, or how many elements are in the list. Let's just look at selection real quick. And they also have different scenarios, like what's the starting state of the list, of the array. So is it just kind of a bunch of random values in there, or is it nearly sorted to begin with, or is it in complete reversed order? A few unique would be like you have a lot of the same values in there multiple times, right? And so we can just take a quick look at selection sort. I think this selection sort, though in the video we saw the selection sort would put it in order. It would go through and find the smallest element and put it at the beginning, and the next smallest element put in the next element, and so forth. I think visually it looks like this one might be basically doing the same thing, but instead of looking for the smallest one, it'll find the largest one, put it at the end, next largest, put it in the end. But it's basically similar, same kind of concept. So you can see it visually. See, it's putting the largest element in the spot, and every time it goes through, it doesn't. It's getting closer and closer. Or was it actually putting the smallest one in there? Yeah, so it was doing that. So it was putting the smallest one in the correct spot. Yeah. So it was similar to how our video algorithm worked, right? And you can see, like in the reversed order, it's having to swap every one of them there, right? But what's cool is once it gets to a certain point, boom, it goes really fast because they're kind of in the right order. How about How about bubble sort? Let's look at a couple of others here, and then we'll run them all together and kind of see them in action in comparison with each other. Oh, okay, yeah. So this one, I remember, it was this one I was thinking of. I think the bubble sort that we saw in the video put the largest one at the end, bubbled the largest elements to the end. I think this one is kind of basically doing the same thing, but bubbling the smallest ones to the beginning. So that's basically working the same way. So you can see it visually. See, it's finding the smallest one, putting it there at the top. So it's bubbling the smallest ones to the top, but it's the same idea. All right, how about insertion sort? So remember, that's the one that shifted things over. So let's see that one. So you can kind of see visually this shifting them down to make room for the new ones. Right. The worst case scenario, I believe, was reversed order, right? Especially the further it goes into the process, you can see it takes longer to shift everything down. And then we looked at merge sort. So what's cool is you can see kind of visually on merge sort, you can see how it's kind of combining things together. So check this out. So it's combining those two, and then it's combining those two, and it's going to combine the whole thing together. So that's a merge sort. So let's see here. Let's change the problem size to 50. And let's go up here. And so these are all the different algorithms that they show visually. We have insertion sort, selection, bubble sort, and merge sort. Those are the ones we looked at. But then they have a few others. They have one called a shell sort, and a heap sort, and a couple different versions of the quick sort. So those are some more sophisticated algorithms. I think at least a few of those are in your book, like in some of the later chapters. Okay. So, and again, they have the different scenarios, different kind of starting states of the list. So let's see visually. Let's run them all at the same time, and we'll get the idea. And it kind of reinforces the idea that what we were talking about before. These big O of n squared algorithms tend to be slower on average than these more sophisticated ones that are more of like the big O log n or whatever it was. All right, so let's let her rip. So insertion sort is done in one scenario, right? In the nearly sorted, but it's still having to turn away in the other situations. And all the other ones on the right are finished except for one scenario for the quick sort, right? While the other ones are still going. So it takes a little while. So poor little bubble sort is still working hard there, in that, especially in that reversed order. It's got to bubble everything, right? So we talk about scalability of algorithms sometimes. So like, when things are small, they might work pretty well, but then if you're talking about sorting like a really, really long list of things, efficiency is important to think about. All right, so with that, I've got this example program that I wrote a while back, and it looks at, it kind of compares these different sorting algorithms against each other. And so what this little program does, it generates a random one-dimensional array of integer numbers. And so I have this function down here called generate arrays, okay? So have I shown you all how to use the random number generator here? Have I shown you in this section? I did in the other section. All right, basically, C++ has this thing called the built-in random number generator that you can use to generate a random number, right? and it'll return a random number from like 0 to some numbers, probably like 32,000 something or other. It's a random integer, right? And you can modify it a little bit if you want to get a random number within a certain range. So here I wanted to get a random number. I wanted to get a possibility of 100 random numbers, okay? And so the rand function here will generate a random number, and if I mod it by 100, that will return a random number from 0 to 99 is what that will do, from 0 to 99. If you want it from 1 to 100, you can just add 1 to it, 1 plus rand mod 100. Right? So you can kind of use the same techniques to get a random number in a certain range or whatever. This line right here, srand time null, that basically will randomize the random number generator, basically. So if you don't do that, you'll get random numbers every time, but you'll get the same random numbers. So it's not really random, right? And so there's this goofy function in C, in the C language, called the time function. And if you do time null like that, it will basically return, it's something goofy like the number of seconds that have elapsed since a certain time, like back in 1980 or something. I can't remember when the starting point is. But the point of it is that number will be different every time, right? Unless you had like two people that ran their program at exactly the same time and had the same exact time on their system clocks and stuff. So I actually had a couple of students that tried to do that a few semesters ago, and they could do it. But anyway, but the point is that this is constantly changing. So it gives it a different starting point every time. So you get different random numbers. Okay. So I declared some arrays back in main, all of size 1,000. So max size is 1,000. And I've got this array called numbers. That's going to be my original unsorted list of numbers, of random numbers. Okay. And to kind of compare the different sorting algorithms, at least bubble selection and insertion sort, those are the ones I compared here. I'm going to take those random numbers and then copy them over to the other arrays, to these other arrays, so they have a good comparison. I'm sorting the same random numbers in each of the three arrays. Okay. So the generate arrays function will do that. So the for loop goes through 1,000 times, or whatever the size of my arrays are, generates a random number and sticks it in the numbers array, and then it copies that number that just generated into the other arrays so that they're all the same. Okay? So that's what generate arrays does. And then what I'm going to do is I'm going to sort the three arrays, the three bubble insertion and selection arrays that are all the same at this point. I'm going to sort them using their corresponding sorting algorithms. And to kind of see how they perform, I'm going to keep track of the number of comparisons that it takes to sort that array and the number of item assignments. So what I define those as, a comparison would be like where it has to compare if two numbers are greater than or less than or whatever. It's going to be an if statement, basically. So this might be different depending on the algorithm. So in a bubble sort, you're basically, you're looking at two consecutive elements in the array, right? So you're having to compare those. So that would be an example of a comparison. An item assignment is where you have to copy the contents of one thing into another spot, right? So in the case of bubble sort, you're probably going to get a lot of item assignments, right? Because it's doing a lot of swapping. And the way I set it up was if it does a swap, that's going to be like 3 item assignments, right? Because it's got to take the item out, put it in the temp, move this one over here, and then move the temp into the other spot. So there'll be like 3 item assignments. So anyway, that's how I did it. Insertion sort is a little bit different because it's got to shift things over. So every time it has to shift something over once, that's an item assignment. So let's take a quick look at some of this code. I'll try not to dwell on it too much, but bubble sort. Let's look at that one first. And I just have a function that will output the arrays. 20 elements on each line. Here is bubble sort. Let's look at that one first. Remember, that's the one that shifts things over. And again, this code is readily available on the internet. It's also in your book, right? So the code for this is not a big secret or anything like that. So basically, and again, I'm not going to, if you take programming 2, we'll focus more on how these algorithms actually work. But basically, the gist of it is you have 2 loops here, right? If you think about bubble sort, it has to make multiple passes through this list, right? The outer loop here is in charge of how many passes it's done, right? And then the inner loop is in charge of actually making the pass through the list, okay? And so, if you remember bubble sort, it looks at consecutive elements. So here's your comparison. If the array at this spot, index, is greater than the element right next to it that has an index of index plus 1, right? That's the one right next to it. If that's true, then you need to swap them. So these 3 steps here will do the swapping, right? So it takes one element, sticks it into a temp, and then takes one spot, puts it in that spot, and takes the temp, put back over there. Okay. And I count that as 3 item assignments because it moves 3 things. So this is keeping track of how many item assignments it's had. Okay. All right, so that is the bubble sort. How about selection sort? That's one that we looked at. Here's selection sort. And I'm doing the same thing. I'm keeping track of the number of comparisons and item assignments. So here, if you think about selection sort, it was going through and focusing on a spot, right? So every time it goes through this outer loop, it's going to be focused on a particular spot. So like, for example, it's going to look at the first spot. So that, and then it starts going through that inner loop. The inner loop goes across to try to find the smallest element. And it keeps track of the index of that smallest element. And then once it finishes the inner loop, it will swap them, right? So the inner loop is in charge of selecting which one it needs to swap with. Then after the inner loop, it swaps them. And then the next time through the outer loop, you're focused on another spot, right? So you're still going to have a lot of comparisons. Here's my comparison counter. But as you can see in the videos, for example, there's a whole lot less item assignments, right? A lot less swapping going on with selection sort because it's after the inner loop. So here's the swap. How about insertion sort? Let's look at that one real quick. Here's insertion sort. It's the one that shifts things over, right? So the outer loop here is basically in charge of of where I am in the list, you know, as far as the sorted or the unsorted portion. And then the inner loop is in charge of shifting things over if necessary. So that's where this do while loop comes in. It will shift things over, right? But again, I've got this item assignment here is when it takes the element out, and then let's see, this item assignment is when it shifts something over. Yeah, and then I've got comparisons there. All right, so that's the insertion sort, right? Let's look at, how about the searches? I'll put those in here as well. So here's sequential search or linear search as they described in the video. It basically just goes through and looks for it, right? So basically it's saying, while I haven't got to the end of the array and I haven't found what I'm looking for, keep going. And just to see, for comparison purposes, I'm going to keep count of how many times or how many spots it's had to look through. Okay. And then I've got the binary search code here. It's really not that much longer, right? But it's so much faster. But again, the key with binary search, it has to be in order already, right? So if it's not sorted, you have to sort it first. So basically, here you can see, like in the video, we keep track of the indexes of the first and last spots, and we calculate the midpoint, right? And then the if statement here will basically test, okay, if the thing at the midpoint is what I'm looking for, great, I found it. So change this found to true. But if it's not, if it's greater, then change the endpoint or the last element, or change the first element if necessary to figure out which half it needs to go and look at. And I also kept track of how many times it has to repeat this process, okay, the search with the search counter. So let's run this and see. And I can make this code available to you if you'd like. All right. So compile and run. So this is the search part of it. So what do you want to search for? Remember, these are numbers from 0 to 99. So how about we choose a number towards, they'll probably be towards the end of these if it was sorted, right? So how about something like 87? How's that? 87. All right, and just I put the search kind of results here. So the number of search steps to find 87 in the first version, the unsorted version, just happened to be 3, right? But basically, I got lucky on that one probably, because 87 probably just happened to be the third, or it happened to be towards the beginning, right? But you can't be guaranteed of that, right? In the sorted, later on I sorted it, and I did a sequential or linear search of the sorted version, and it was at spot 875. So it took 875 iterations through that loop to find it, because it was towards the end, right? But in the binary search of the sorted list, it took 3. So that's really, really fast, right? I just happened to get lucky on that one. See, and I have my results here in an output file, sorting output. So you can see it just happened to be at the beginning of the unsorted original, the random array. But if I were to run this again, it might not be. So let me just do it again. So it was later on that time in spot 73. But look at binary search. It still only took three times to find it. Right. All right, so let's take a look at some of our results. So what I did here's my original unsorted array that's random. And then here is which one is this? This is the bubble sorted version. Okay, so you can see now it's sorted. And it took 499,500 key comparisons in that process, or comparisons in there. And sure enough, in the book, they'll tell you kind of on average how many comparisons bubble sort should take. And it's probably like n squared divided by 2 or something like that, right? We had a lot more item assignments, right? Look how many item assignments, because it's got to do all the swapping and stuff, you know. There's a lot of swapping going on. And this version of the bubble sort that I have here is not as smart as the one in the video. I didn't have the swap counter and stuff like that. If I were to change it to that, the number of item assignments I'm guessing would probably be lower, and the comparisons might be a little bit lower too. Here's insertion sort. All right, so insertion sort is also sorted them, right? It took only about around half of the number of key comparisons as bubble sort, right? So around 256,000 comparisons and swaps or item assignments, right? This is the one that shifts things over. And then here is selection sort, right? Also put it in order. Also took around 500,000 comparisons, but look at the number of item assignments. It's a lot less, right? And you think about it, selection sort, that's what it does, right? It selects, it doesn't swap a whole bunch of stuff. It selects what it needs to swap and then swaps them. So the number of swaps is about the same number as the size, right? The size was 1,000, so I've got about 1,000 swaps, but each swap, I counted that as 3 item assignments, so it's around 3,000, right? Anyway, I thought that was kind of interesting. And then here is some search results. 87 is found at position 72 in the unsorted one, and then towards 871. But that was just some other stuff. I can't remember exactly what I was doing there. So, anyway, so hopefully that illustrates it a little bit more. If you ever have to put things in order, and we'll be doing that some in programming fundamentals too next semester. We'll revisit these algorithms towards the beginning of the semester. All right, cool. Well, that's it for that.